So what if the universe's ultimate speed limit isn't actually about speed at all? What if it's the fundamental rule that's keeping reality itself from completely falling apart? Now, I'm not sure if we all do, but some of us dream of exploring the stars, zipping across the galaxy in an instant, just like we do in the movies. But there's this incredibly annoying rule. I don't know if you've heard of it. It's called the speed of light. 299,792,458 meters per second. No more. That's it. That's all we get. It feels less like a physical law and more like a cosmic roadblock. But why? Why can't we just build a bigger engine and go faster? But understanding the why this limit exists actually changes how you see everything. It's not like the sound barrier, which we did eventually break because humans are awesome sometimes. It's much, much deeper. So today on the ARQIV, we're diving into the light barrier. We'll look at why Einstein realized it's impossible to cross that. And we're going to explore the weird, fascinating science of things like warp drives and wormholes. And we'll confront the very real possibility that exceeding the speed of light doesn't just mean going fast. It means traveling backwards in time. Thanks for tuning into the ARQIV today. I'm your host, Steve, a science enthusiast and also researching topics about science and tech that you don't have to. Now, I love digging into these type of questions that reshape how we understand the universe, and this one to me has always been one of those things that just keeps lingering around because this to me is fundamental. Why is the speed of light the limit? Now, to understand this, I had to go back to the early 1900s because physics was having kind of a crisis if you don't know. We had Newton's laws of motion, which worked great for apples and planets, and we had James Clerk Maxwell's law of electromagnetism, which explained light. But the problem, they didn't agree. Now, Maxwell's equations predicted that the speed of light should be constant. Always. It didn't matter if the source of the light was moving towards you or away from you. But humans, it makes no sense intuitively, right? Because if we're driving at 50 miles an hour and I throw a baseball forward at 10 miles an hour, you standing on the ground see the ball moving at 60 miles an hour. At least that's how it goes in my head, right? But if I shine a flashlight, you don't see the speed of light plus 50 miles an hour. You just see the speed of light. And I, in the car, also just see the speed of light. Now, how can we both measure the same speed for the same beam of light when we are moving relative to each other? Enter Einstein and special relativity. Einstein made a radical choice. He sided with Maxwell. He said, all right, the speed of light is constant for everyone. Cool. But for that to be true, something else has to give. And the things that gave were the absolute concepts of this little thing we call space and time. Because if speed is the distance over time and the speed of light has to stay the same, then our measurements of distance and time must change depending on how we're moving, right? Now, this is where we get some famous stuff, some famous effects in science like time dilation and length contraction. For those sci-fi fans out there, you know what I'm talking about. If you're moving very fast relative to me, I perceive your time slowing down and your length shrinking. And these are not actual illusions. They are real physical effects. Space and time, they're not separate stages where the universe plays out. They are woven together into a single four-dimensional continuum, space-time. All right, so the first pillar, if you will, of the light barrier is this speed of light. We'll call it c. Isn't just a property of photons, it's the constant that defines the very geometry of space-time. It's the cosmic conversion factor between space and time. But let's talk about the energy cost. Now, I know space-time is weird, but what physically stops me, myself, from accelerating past c? And the answer is mass and energy. This equation E equals mc squared, tells us that mass and energy are two sides of the same coin. When you accelerate an object, you give it kinetic energy. But in relativity, that added energy also adds to an object's mass, what we call its relativistic mass. Think of trying to push a shopping cart. It's easy at first, but as you push it faster, adding energy, it's as if the universe is secretly filling the cart with bricks. The faster you go, the heavier that cart gets, and also the harder it is to push it any faster. So as your velocity approaches the speed of light, in this case, the math shows that your relativistic mass approaches infinity and not beyond. And here is the thing that kicks it. To accelerate an infinite mass, you would need an infinite amount of energy. Since we don't have infinite energy, at least not that I'm aware of, we can never reach the speed of light. We see this in particle accelerators like the Large Hadron Collider. We can get protons to like 99.9999991% the speed of light, but we can never hit 100% because the energy cost just skyrockets. It's not a wall that you actually hit, it's an asymptote, a horizon you can approach forever, but honestly, you could never reach. But wait, there's more. There's actually a third reason for the speed of light. And honestly, it's the most profound reason. It's called causality. You know, cause and effect. The speed of light is really the speed of causality. It's the maximum speed at which any cause can propagate an effect through the universe. So to visualize this, physicists use something called a light cone. Now, a light cone is just a 3D visualization of a light in a cone shape. An event happens at the center of the vertex, and the upper cone is the future, and the lower cone part is the past. So imagine an event. Let's say a star explodes. The future light cone contains all of the places in space-time that this event can actually influence. The boundaries of the cone are actually defined by how fast light can travel from that explosion. So anything outside of that cone is elsewhere. The explosion cannot affect anything in the elsewhere because the influence would have to travel faster than light. So here's where it gets weird. I honestly don't know how else to say it, but space and time are relative. Observers moving at different speeds will disagree on the timing of events. If you could travel faster than light, you would break this structure. Okay, now let's say I send a faster than light signal to a friend on Mars. Now, in my frame of reference, the signal arrives after I send it. But according to the math of relativity, there would exist another valid observer, maybe perhaps flying past Earth in a spaceship, who would see the signal arrive on Mars before I sent it. So if effects can happen before their cause, the universe stops making sense. But you could build what physicists call a tachyonic anti-telephone. Man, that word was hard to say. I could send an FTL, a faster than light message today that tells myself yesterday not to send the message. Wicked. So then the question becomes, did I send the message or not? So this creates irresolvable logical paradoxes, the classic grandfather paradox, if you know what that is. The universe seems to abhor a paradox. To preserve the logical consistency of reality, the structure of space-time forbids any form of FTL travel or communication. The geometry of space-time, the infinite energy barrier, and the need for causality, they're all locked. I mean, they're interlocked. They're in it for life. You can't break one without shattering the entire framework of reality. Now, hearing all that, I mean, the rules are strict. But if you read science news, you constantly hear about things that seem to break this limit. So let's tackle the big two. The first one being the expanding universe. Because we know the universe is expanding. Distant galaxies are moving away from us. And the further away they are, the faster they recede. Because in fact, galaxies beyond a certain distance, about 14 billion light years away, are receding faster from us than the speed of light. Here's a visualization of galaxies moving away with speed vectors increasing with the distance, eventually exceeding the speed of light. And you may be asking yourself, whoa, hold up, how is that possible? I mean, did we just contradict everything I just said? Well, this is the difference between special relativity, which governs motion through space-time, and general relativity, which governs the dynamics of space-time itself. What? Okay, let me try to break that down because the speed limit c only applies locally. So in any small patch of space, nothing can move past another object faster than light. But the distant galaxies, they aren't flying through space at FTL speeds. Instead, hang on with me here, the very fabric of space-time between us and them is stretching. The classic analogy is raisins in a loaf of baking bread. I mean, check out this animation of a raisin bread expanding. The raisins move apart without moving through the dough. And as the dough expands, the raisins keep moving further apart. The further apart the two raisins are, the faster they separate, but the raisins themselves aren't moving through the dough. The space between them is ever increasing. So in this analogy, the galaxies are the raisins, and space-time obviously is the dough. Because this is the expansion of space and not motion through space, it actually doesn't violate the cosmic speed limit because we can't use this expansion to send a signal faster than light. So then, what about things like quantum mechanics? I know the quantum word. Here we go. The famous spooky action at a distance. You take two particles and you entangle them. You separate them, one on Earth, one on the other side of the galaxy. And when you measure a property of the particle on Earth, say it spins, you instantly know the state of the other particle. Now, this correlation is instantaneous, faster than light. But then again, doesn't this break the speed of causality? Can't we use this for FTL? That's a really good question. The answer, in short, is no. And the reason is crucial. Randomness. It's codified in the no communication theorem. The outcome of a quantum measurement is fundamentally random. I can't force my particle to be spin up to send a message. I just measure it and get a random result. I mean, yeah, the other particle instantly correlates that, does the same thing, I know what it's going to do, but the person on the other end just sees a random result too. The correlation only becomes apparent when we compare our list of results, later. And to compare those lists, we have to use a conventional communication channel like radio waves, which is limited by the speed of light. Now, entanglement is instantaneous correlation, but it is not a transmission of information. So the light barrier, that thing is robust. But scientists are a curious bunch, and they can't help but ask, are there any loopholes to the laws of physics? All right, so let's take a deep dive in this. Let's look at the three main theoretical ideas for FTL travel. And first, we're going to start off with everybody's sci-fi favorite, tachyons. The most straightforward idea is, what if there are particles that just always travel faster than light? These hypothetical particles are called tachyons. A tachyon would be a mirror image of normal matter. It would take infinite energy to slow them down to the speed of light because they would lose energy as they speed up. But they have some major problems. To make this type of math work, they need to have an imaginary mass, which is weird. And more importantly, they violate causality because bringing back those time-traveling paradoxes, that's what would happen. In modern physics, the concept of tachyonic field isn't interpreted as an FTL particle anymore. It's seen as a sign of instability in the vacuum of space-time. The Higgs field is actually a really great example of this process because it underwent tachyon condensation to give particle mass, but it doesn't actually involve FTL travel. So tachyons, though cool as stable particles, are largely dismissed. But hold on, I heard of another sci-fi theory myself, and it's called wormholes or the Einstein-Rosen bridge. Because if we can't go faster than light through space, what if we could take a shortcut? And this is where wormholes come in. It's just basically a tunnel connecting two distant points in space-time. I said basically. I love it. Oh, here we go. Here is the classic analogy, basically, of a wormhole. You know, you've seen it in Interstellar and other things too, but flat sheet of paper folded and a pencil smushed through it. That's connecting two distant points, right? Wormholes are actually valid mathematical solutions to Einstein's equations of general relativity. The original concept, the Einstein-Rosen bridge, connected a black hole to a theoretical white hole. But with this, there's still a problem. Those kind of things are actually incredibly unstable. They collapse almost instantly. And faster than a beam of light could actually pass through them, they'd be gone. So to make a wormhole traversable, you have to prop the throat up against the immense gravitational force that's actually trying to close it. And this requires something strange and unusual, something that pushes space-time apart instead of pulling it together. But we'll get back to that in just a minute, so hold tight, because we're going to jump next into the most ultimate sci-fi trope, and it's called the warp drive, the Alcubierre drive. So this one is everyone's favorite. I love it because it was inspired by Star Trek. Theoretical physicist Miguel Alcubierre, hopefully I said that right, proposed this in 1994, the Alcubierre drive. It doesn't move the ship through space, it moves space around the ship. So basically space-time contracts in front of this ship and expands behind it, pushing the bubble forward. That actually creates a warp bubble of flat, normal space-time around the spacecraft. The drive then contracts space-time in front of the bubble and expands space-time rapidly behind it. So the ship essentially is riding this wave in the fabric of reality. Dude, that sounds cool. This is brilliant because it circumvents the local speed limit. Inside this bubble, the ship is at rest. It actually feels no acceleration. Time in that bubble actually passes normally. If you fired a laser inside the bubble, it would move at c. C, there you go, c, relative to you. But from the outside, the bubble itself can move at theoretically unlimited speeds. It's like being on a surfboard. You aren't moving relative to the water immediately around you, but the wave is carrying you forward at really high speeds. Now I know, wormholes and warp drives, man, they sound amazing. And they are, mathematically speaking. So they're consistent with general relativity, so why aren't we building them? That's actually a pretty easy answer because both concepts share this one thing, this potentially unsurmountable obstacle. They kind of require a key ingredient that we've never seen and don't know how to actually make. Also another sci-fi trope, and it's called exotic matter. Now, if you're wondering what exotic matter is, you're at the right place because I'm going to tell you. It's a substance with negative energy density, or negative mass. Because normal matter has positive energy and creates attractive gravity. But exotic matter would have negative energy and create repulsive gravity, or commonly known as anti-gravity. This anti-gravity repulsive force is exactly what you need to prop open a wormhole or create the space-time distortions for something like a warp drive. Now, this isn't antimatter, because antimatter has positive mass and falls down just like regular matter. The thing with exotic matter that makes it really truly bizarre is if you pushed it, it would accelerate towards you, not away from you. Think about that. But another question is this like a math thing, or do we know if it actually exists? I love this word, theoretically, maybe, because quantum mechanics predicts something called the Casimir effect. If you put two metal plates very close together in a vacuum, the energy density between them becomes slightly negative. But this is very microscopic. It's a microscopic effect. The amount of negative energy is minuscule. And to do something like stabilize a wormhole or power a warp drive, man, the energy requirements are astronomical. Initial calculations for this Alcubierre drive, Alcubierre, man, I hope that guy doesn't get mad at me, This suggests you need an amount of negative energy equivalent to the mass of something like the planet Jupiter. That's kind of on the light side because others calculate that you need energy that's bigger than the entire observable universe. Now, while the models have been refined, the requirement for vast quantities of substance we don't even know exist, that's a pretty huge roadblock. Even if, and that is a big if we did find it, these FTL methods still have issues. I mean, they are effectively time machines, bringing back those kind of causality problems that we had at the beginning of this. There's also this thing called the horizon problem. So with the warp drive, you can't control the front of the bubble. So in essence, you can't steer the ship. And theoretical models suggest that a warp drive, upon arriving at its destination, would release this big, massive blast of high energy particles accumulated during the entire journey. I mean, and it could potentially annihilate the entire destination that they were going to. So, there's that. The speed of light stands as a fundamental limit, not because we lack the technology, but because it is an intrinsic feature of the causal and geometric structure of our universe. It's the speed of causality. It's the rule that keeps the universe logical, ensuring that cause always comes before the effect. So the dreams of FTL travel, that faster than light travel dream, of going through wormholes and warp drives, I mean, they all look really good mathematically, but they hinge on the existence of stuff like exotic matter and that substance that might be forbidden by a more complete theory of physics that unifies gravity and quantum mechanics. It's all really humbling, isn't it? Because the universe, it has rules, and while it might mean we are destined to explore the cosmos at sublight speeds, there's still that quest to understand these rules, to push the boundaries of what's possible within the framework of our own reality. And that's what science really is all about. We're learning new things every day, and who knows, maybe one day we might crack it. But it does mean the universe is far vaster and perhaps far stranger than we could have ever imagined. I appreciate all of you joining me today on this weird question research analysis. And if you enjoyed exploring the frontiers of this type of physics, be sure to subscribe and let me know in the comments what cosmic mysteries you want us to tackle next. Until then, I'll see you next time.